Welcome back. I'm Warren Powell. This is a universal modeling framework for sequential decision problems, bridging machine learning and stochastic optimization, part 3. So in part 2, I talked about evaluating a policy and how to set that up as the objective function for policy evaluation, but I didn't say anything about how we actually start to design policies. Part 3 here will be dedicated to the issue of how do we actually search over policies. So we're going to start with, what is a policy? I get this question a lot. A policy is a method that makes a decision using the information in a state variable, any method. So I'm up to almost 50 words in the English language, any one of which means how to make a decision, in the right context. Now, to help understand this, I'm going to develop a bridge between machine learning and sequential decisions. In machine learning, I'm searching over functions. Now, they can be different types of functions, and I have tunable parameters. Sequential decisions, I'm searching over functions. They're policies. In machine learning, I have a training data set to fit some function f to the training data set. And in sequential decisions, I don't have a training data set. I require an objective function that tells me how well I'm doing, and the state transition model that tells me how systems evolve over time. That's where the physics of the problem exists. So now what we have to do is address the question, how do I search over policies? So there are two fundamental strategies for designing a policy. The policy search strategy takes some function that does not plan into the future and tunes it to make it work well over time. The look ahead does plan into the future to make decisions now. Both of these strategies I'm going to divide into two classes, creating the four classes of policies. So let's start with policy search. The first of them, policy function approximations. These are analytical functions that specify what to do given what we know. It can be an order up to policy. It can be buy low, sell high. What if it's cold, wear a coat. It could be any lookup table, linear and nonlinear model, neural network, any function that you might use in machine learning. Now, the PFAs of the four classes of policies, it's the only class that does not involve an embedded optimization problem. Okay, cost function approximations. I'm going to divide these into two categories. One is where X is a discrete choice, like choices A through G. And maybe I have a value of the choice, the estimated value. And I could just say, well, just take the one with the best estimated value. And a lot of people do this. But there is an uncertainty, and I may not know it very well. So let's say I have a standard deviation. And so possibly I'm going to take a tunable parameter theta, multiply times the standard deviation, add it to my estimate. Now, that's an optimization problem. Now, that's not the only way to solve this problem, but cost function approximation has an optimization problem. Here, it's just a sort, okay? And there's a tunable parameter. Now, if X is a vector, instead of doing a sort, I might be solving a linear, nonlinear integer program, a math program. So I'm going to have a math programming problem that maybe I've adjusted in some way. I went over this early in the talk. And maybe there's tunable parameters. Usually there's tunable parameters. Now we can tune the parameters in the objective function we described in the previous part. So we have the policy and the problem. Now, CFAs are actually quite popular in industry. Airlines optimize schedules using schedule slack to handle weather uncertainty. Manufacturers use buffer stocks to hedge against production delays. I can optimize the location of distribution centers and warehouses, but I want to do this in a way that understands that the demand might have surges. Grid operators who manage the power grid will sit on Monday, plan for an uncertain Tuesday, and they put buffers various places. It was working with a grid operator that I came up with this idea because I realized how powerful it was. You won't find CFAs in any of the standard textbooks, any of the older textbooks, but it is a widely used technique just in an ad hoc way in industry. Now, PFAs and CFAs generally have tunable parameters because this is what you do to make them work well over time. Now, evaluating a policy is almost always noisy. Maybe I'm doing it in a simulator, maybe I'm doing it in the field. Now, whenever you're doing it, I can tune theta using a derivative-based method. This is itself a sequential decision problem where the decision is the step size. Or I can have derivative-free stochastic search where the decision is, hey, what part of the function should I sample next? These are both their own sequential decision problems, which is a lot of fun to think about. So let's go to look-ahead approximations. I like to start off with this picture of Dorothy and the Wizard of Oz, where she has to get to the city of Oz to find the wizard, and she has to pick which direction to go. Now, in order to make this decision, she has to balance between an immediate cost or contribution and then all this messy, ugly stuff in the future that depends on all the uncertainties of her path. And clearly, this is a very ugly piece of mathematics, and it would be nice to throw up our hands and say, oh, well, we can never compute this. Let's just ignore it. But sadly, we cannot do that because there are problems where we need to at least approximate this in some way. Let me just illustrate it with a decision tree where we start off at a decision node. That decision node represents the state, that's what we know. Now the decisions here in a picture, I've got three actions, buy, sell, or hold, for example. But X could be a vector, could be a very large vector. And I want to choose the best X, but I have to anticipate that depending on what X I choose, there's random events that could happen. I have to average over these. Now I go into the future. Now, as we walk into the future, there's places where I have to make decisions, which I'm going to have to do with some policy. And then there's going to be more uncertainties. Now, no doubt, all that future stuff is going to be a computational nightmare. So we're going to approach that with two more classes of policies. The first one is that I'm going to take this piece of the function and say, well, this whole thing is a function of where I am at time t plus 1, the state at time t plus 1. Let's just call it a value function. And Bellman came along in the 1950s and says, well, if the state happens to be discrete, and if there's not too many of these discrete states, we can actually compute that value function exactly. And we've had decades of research that are continuing to this day, but the simple fact is this doesn't apply to very many problems. That expectation is also impossible to compute for most real applications. Now down here, so this is the work that I did early in my career. First thing I did was get rid of the expectation by moving from the state to the post-decision state. So SX is the state after I've made a decision before any new information. Now that value function, I cannot compute it exactly, so I'm going to use machine learning methods. So using machine learning methods dates back to the 1970s. The optimal control community did it. In the 1980s, computer scientists, Sutton and Bartow, picked it up. They called it reinforcement learning. In the 1990s, other communities, especially in OR, picked up on it, doing it with machine learning. Now, something that I found, generally that X is supposed to be something simple, one of a set of discrete actions. But in fact, if you get rid of the expectation, we now have a deterministic optimization problem, and that V bar is a function that I control, and as long as I do it in a convenient way, I might have a math program that I can solve, and now X can be a vector, it can be a very large vector. So now we've opened up the door to using dynamic programming for solving very high-dimensional problems. And here's an example of one. We've actually got this in production at Optimal Dynamics where we have a set of trucks, and it can be 4 trucks or 400 trucks or 4,000. The hard part is not having thousands of trucks. The hard part is that when I make a decision on Monday, it can impact the problem on Tuesday, and then that impacts the problem on Wednesday. And as I roll forward in time, I've got loads being called in. This is a very high-dimensional random vector. The idea, even solving this problem deterministically into the future is hard. Now, what we're going to do is to say, well, let's just take Monday and then come up with an estimated and approximate value of the driver in the future. These are value function approximations. For the math programmers in the audience, this is an estimate of a dual variable. Now I've got an optimization problem that actually isn't too hard to solve. Now here is a different network. This is actually a network that was being solved back in 1980. I think they still use it, or some version of it, by Schneider National. It was a pioneering company. Now this network optimizes at the same level of detail over the whole horizon. It cannot handle individual drivers. It cannot handle uncertainty. What it can do is it can optimize over time, which is still quite hard. This is a model. and I could choose this model. Schneider National got great use out of it, but then they ended up with a question that this couldn't solve. My approach was to say, let's model every individual driver at a point in time and use value function approximations to approximate their values in the future. Now, this is very easy to solve, and I can simulate forward in time following a sample path and then do that iteratively. And over these iterations is where I'm going to learn the value functions. Now, this problem I solve at each point in time is a deterministic integer program. And we use a standard solver at Optimal Dynamics. Right now we're solving about 5 million of these deterministic integer programs to solve what is a very stochastic problem. And this is a problem that cannot be approximated deterministically if we want to keep the characteristics of each individual driver. Now, here are simulations for 11 different trucking companies. This is real data. In the beginning, this is where all the value functions are equal to 0, and then after 15 iterations, I've optimized them. Now, here's a particular carrier, these blue dots. Every blue dot represents the value of everything that happens over a 2-week simulations, solving 14 or maybe about 28 different deterministic integer programs, and somehow the results are getting better and better, even though each blue dot is the sum of the results of an optimal solution. What we're doing is we're changing the model, and we're changing the model so it works well over time. And for some carriers, we get a very significant improvement, up to 40 or 50% improvements in profits. Now, because we are modeling every individual driver, an output of this could be a simulation. We call this SmartTL. We're very dependent on this. We tune this for every individual carrier, and we can model all the detailed work rules. By the way, and everything's running here in continuous time, not in discrete time. Okay, now we're down to the fourth class of policy. Sometimes I have to plan into the future. Great example. Here is Google Maps. I'm up in the upper right-hand corner in Hartford, Connecticut, trying to get down to Princeton in the lower left-hand corner. There's Google Maps using a deterministic look ahead. It's doing point estimates of travel times, and it's got this great trip right through New York City. Okay, so Google Maps says that's best. Of course, I'm sitting there going, okay, wait a minute, that looks very problematic. Now, what Google Maps does is it solves an approximate look ahead. So down here, let's state at time t, so let's say at 4 p.m. when I'm getting ready to move, state st would capture the best estimates of all the travel times on the network. X is my shortest path. WT plus 1 is as I take off and I drive for a little while, that captures all the updated estimates of travel time that Google's constantly getting. Now, when Google finds the shortest path, it's planning into the future. It's also solving a sequential decision problem, but we're going to introduce approximations, and that's why all the tildes are there, and every variable has 2 time indices. The first time index t is the time at which I'm solving the look ahead. So for example, when I start my trip at 4 p.m., this would be my 4 p.m. snapshot. And then t prime is as I plan into the future. Now, putting together these approximations, there's a number of ways to approximate the look ahead, and this is a true art form. And this is something where you have to understand the nature of your problem, because the right way to do the approximation is not the same for everyone. I have to understand, I don't want to approximate away very important characteristics of my problem, but I also have to think about how hard it is computationally and how much time I have. So let's say I come up with an approximation that I think will work. I can compute it. I can do it fast enough. I think I'm going to get good results. So I solve my approximation time t, update, do it again at t plus 1, update, do it again at t plus 2. Now I have a policy. It's a direct look-ahead approximation type of policy. Now, these direct look-ahead approximations, the controls community calls it model predictive control. Now, MPC in the controls community is almost always interpreted as a deterministic look-ahead, but technically MPC is any type of look-ahead that uses a model to plan into the future. Now, here we have Google Maps with its deterministic model running through New York City. I, the user, is saying, oh, that looks really risky to me. Google Maps, of course, gives me an alternate route, And I'm like, look, maybe New York, going through New York City on average might be good, but I'm worried about the risk. What I'm doing is in an ad hoc way, I'm using this idea called robust optimization. Now, I could use a decision tree. I can use approximate dynamic programming, which is, we actually do that at Optimal Dynamics, or stochastic programming with the scenario trees that was first introduced by Danzig back in 1955. Okay, deep breath. We've covered all four classes of policies. The policy search class are the simplest, the PFAs and the CFAs. And then we have the look-ahead policies, the VFAs based on Bellman's equation, and then the direct look-aheads, which can be a deterministic or stochastic look-ahead. We've illustrated all four of these using different settings. All of these are policies that are actually being used. I could actually claim that most humans, without realizing it, I can come up with problems where when I look at how they're solving the problem, I'm going to say, yes, they actually did a direct look ahead, or they actually used a value function approximation. Now, three of the four classes of policies involve optimization problems, and this can be very confusing. As you have the policy, it's an optimization problem, you solve the optimization problem, and you think you're done. I've optimized, and it's optimal. But you have to understand that very often these are used over time. So in other words, the optimal solution at a point in time does not mean you have an optimal policy. Now I'm going to make a big claim. I'm going to claim these four classes of policies are universal. They cover every method for making decisions described in the research literature or used in practice, including methods that haven't even been invented yet. In other words, these are meta classes. I don't have four pieces of software to solve every possible problem. Each meta class opens up its own array, especially the direct look aheads. But it does mean that if you go into a company, whatever they're doing, it will already fit in the framework. And that's a great idea because now you can start from an initial basis and then move from there. Now, you can also do hybrids. You can do mix and match. And again, I will claim that we humans often use hybrids. We might do a look ahead and then use some estimate of a value to keep it from getting too complicated. Okay, so now I've reviewed the policies, and hopefully we have an idea of what it means to search over policies. This is the end of part 3, and I hope you'll move on to part 4.